All right, we are in section 10.6, parametric equations, page 979, 10.6, parametric, I'm just going to say parametric equations. It's actually entitled plane curves and parametric equations. So, a lot of times when we describe something in motion, right? If we have an object moving along a path, well, I can describe the object's position. So suppose this is oriented in some XY system, all right? So I can describe that object's position, right? But it'd be really nice if not only I knew the object's position, but I also knew the time when it was at that point. Because if this is a video game and I'm trying to kill something, not only do I need to know where it was at, I only need to know where it was at and when it was there, right? So sometimes we want to know the thing's position and maybe we want to know time. So time and position. Well, this kind of gets us to parametric equations, okay? This kind of leads us into plane curves and parametric equations. So they say that f and g be functions, of t over an interval I. That f and g be functions over an interval I. Okay? This definition is on page 979. The set of points defined by x comma y equals f of t g of t. Set of points x comma y equals f of t g of t. Okay? It's called a plane curve. So we're defining what we mean by a plane curve. Okay? The equations, x equals f of t and y equals g of t. Are called parametric equations of the curve, and t is the parameter. Parametric equations of the curve, and t is the parameter. Parametric equations of the curve, and t is the parameter. Okay? So there's our definition of parametric equations. Okay? Well, so example one, they say sketch the, I'm just going to say sketch. It says sketch the plane curve. I'm just going to say sketch. They give me a plane curve, x equals t squared minus 2t. And y equals t minus 2. And then they say over, they give me an interval, they got to give me an interval, t greater than or equal to negative 2, less than 3. T greater than or equal to negative 2, less than 3. So they want me to sketch that plane curve over that interval. Well, nothing hard about it. Now, one thing about parametric equations, we're going to sketch this thing in the xy plane just like any other function, but not only do you have to sketch the graph, but when something is described with parametric equations, you have to sketch the graph and you have to indicate the orientation, the direction that you're moving as t increases, in that case from negative 2 to 3. So we're going to create a little chart, t, x, and y. And we're just going to use those values to t. We're going to use negative t, negative 1, 0, t can be 0, t can be 1, t can be 2, t can be 3. Now I'm going to use 3 even though t is strictly less than 3. So that point, when I get to t equals 3, that point won't actually exist. I'm going to put an open circle there, but I'll need to know where to place the open circle. So, x is t squared minus 2t. So when t is negative 2, x would be negative 2 squared minus 2 times negative 2. All we're doing is putting a negative 2 everywhere we have an x. Okay? Negative 2 squared is 4. Negative times a negative makes plus 4. That's 8. Well, y is just t minus 2. So when x is negative 2, y would be negative 2 minus 2. Negative 4. Okay? So all we're doing is plugging these respective values into here and here, because that's the definition for y, that's the definition for x. Let's do one more. When t is negative 1, I'll have negative 1 squared minus 2 times negative 1. Negative 1 squared is 1. Negative times a negative makes plus 2. That's 3. Put the negative 4 in for the y. Y would be, put a negative 1 everywhere you have a t. Negative 1 minus 2, that's negative 3. Well, keep this process up, okay? Keep this process up. So I had 3, negative 3. When t is 0, you'll get 0, negative 2. When t is 1, you'll get negative 1, negative 1. When t is 2, you'll get 0, 0. And when t is 3, you'll get 3, 1. Okay? All we're doing is plugging into those equations these respective values of t. So I'm not going to do all those details. That's just arithmetic. All right. So let's sketch the graph. There's the x-axis. There's the y-axis. X's go, I see from a negative 1 and I see all the way up to 8. So 1, 2, 3, 4, 5, 6, 7, 8. 3. The y's go from 0 to negative 4, maybe. Okay? So 8 comma negative 4. 8, negative 4, right here. 3, negative 3, I go over 3, negative 3, right here. 0, negative 2. All I'm doing is the x and y coordinates. 0, x is 0, y is negative 2. That's right here. Negative 1, negative 1. Negative 1, negative 1, right here. 0, 0, right here. 3, 1. Now remember, this was at t equals 3. 3, 1, I go over 3 not 1, but I put an open circle there. That's not a filled-in point because t was supposed to be strictly less than 3. Okay? So I can't put a solid point there. So we clearly see that the graph does this. And again, you have to indicate orientation. As t increases, I'm traveling this direction along that curve. With parametric equations, you have to sketch the curve and you have to indicate the direction of motion. Okay? All right. The next thing is eliminating the parameter. Eliminating the parameter. Okay? Very, very, very simple process. Eliminate the parameter. Eliminate the parameter. We're on page 9-8. Okay? Let's just do one. Example 2, eliminate the parameter. So, we call it 8. They give me parametric equations. X is the square root of t. X is the square root of t. Y is t minus 4. Okay? X is the square root of t, y is t minus 4. Well, if x is the square root of t, if I square both sides of this thing, x squared would be t. If x equals square root of t, square x, you'll get x squared. Square the square root of t, you get t. So in place of t and y, I can write x squared. So y would be x squared minus 4. Y would be x squared minus 4. Now, you've got to be careful with these parameters. X was the square root of t, so x was always non-negative because the square root can never be negative. Okay? This thing, if you recall, y equals x squared minus 4. That's the x and that's the y-axis. -1, -2, -3, and -4. That's a parabola that does this. That's y equals x squared minus 4. But since x was positive, it's really just this half. X is square root of t. The square root of something can only be positive, right? 0 or positive. So really it's only that half. So I have to say with this, I have to put the restriction, x can only be bigger than or equal to 0. Because of that original definition, my parametric definition of x. X was the square root of t, so hence x has to be greater than or equal to 0. X can never be negative. So when I rewrite this thing and eliminate my parameter, I have to add that condition that x is positive or non-negative. Because the square root can never be negative. Okay? And B says sketch the curve and indicate its orientation. Well, there's the curve. Okay? There's the curve, y equals x squared plus 4. But the question is, am I moving that direction down there, or am I moving that direction? Well, t, x, and y. Let's see. Well, we said t has to be 0 or bigger. So when t was 0, x was 0. Put a 0 here, you get -4. So 0, -4, that means you're starting right here. X is 0, y is -4. That's this point right here. When t is maybe 1, x is square root of 1, which is 1. When t is 1, 1 minus 4 makes -3. So 1, -3, you're right here. So that means that we are traveling this direction on this curve. Again, with parametric equation, you have to sketch the thing, sketch the curve, the plane curve, and you have to indicate orientation. What direction am I traveling along the curve? So you're starting at 0, -4, and you're traveling up. Example 3, eliminate the parameter. So I call this A, eliminate the parameter. I'm just going to call it B. Eliminate the parameter. Okay? Well, this one says x equals -2 sine theta, and it says y equals 2 cosine theta. So same directions. We're going to eliminate the parameter, we're going to sketch the plane curve, and we're going to indicate orientation. Eliminate the parameter, sketch the plane curve, and indicate orientation. Well, these are trig functions. What if I did x squared plus y squared? That means x gets squared, the y gets squared. Okay? But -2 sine theta squared becomes 4 sine squared theta, plus 2 cosine theta squared becomes 4 cosine squared theta. Pull out the 4. Okay? Pull out the 4, you get that. That should look familiar. That's one of those Pythagorean identities. The sine squared theta plus the cosine squared theta is 1. So x squared plus y squared equals 4. That would be the corresponding rectangular equation. We've eliminated the parameter. We've eliminated the parameter. We get x squared plus y squared equals 4. Well, you should recognize that. That's a circle of radius 2 centered at the origin. That's a circle of radius 2 centered at the origin. So draw a circle, radius 2 centered at the origin. So pretend that's 2, that's 2, that's -2, that's 2. -2, okay? There's my x, my y-axis. A circle, pretend it's a circle, I know it doesn't look like one. A circle centered at the origin. Now, so I've got the curve, but again, you have to indicate orientation. As t increases, this was my parametric definition. As t, No, this one, I'm sorry. We're doing this one. This is my parametric definition. My parameter is theta. In this one, the parameter was t. In this one, the parameter is theta. Whatever the x and y terms are written in terms of, that's the parameter. So my parameter is now theta. So the question is, for that circle, am I traveling counterclockwise on the circle or am I traveling clockwise on the circle? Okay? Well, to figure that out, all you got to do is get a couple angles. So theta, and I'm going to use angles since we have trig functions. So theta, x, y. So when theta equals 0, x would be -2 sine of 0. Well, the sine of 0 is 0. So the x-coordinate is 0. Y would be -2 cosine of 0. But the cosine of 0 from your unit circle is 1, so that's -2. So 0, -2. We're starting at 0, -2. That's right here. But again, the question is, am I traveling that direction around the circle, or do I start here and travel that direction? I need one more point to figure that out. So let's just choose something nice. I'm going to choose power 2. So now, x would be -2 sine of power 2. Sine of power 2 is 1, so that's -2. Y would be 2 cosine power 2. Cosine of power 2 is 0. So we get -2, 0. The x-coordinate is -2. The y-coordinate is 0. So we started here, and now we're here. So that means we're going in this direction around that circle. So again, with parametric equations, you have to sketch the plane curve, and you have to determine orientation. Which direction am I traveling along that plane curve? And for us, we are traveling clockwise around that circle. So it's that easy. It's that easy to eliminate a parameter and to determine orientation. Nothing hard about it. All right. So we've learned a little bit about these parametric equations. And again, there's a bunch of different ways to parameterize a given set of equations, a given x and y, right? Let's just do another example, and we're going to look at 3 different ways to parameterize the same curve. We're going to look at 3 different ways to parameterize the same curve, and we're going to look at the differences. Okay? We're going to look at the differences. So, this is example 4 on page 982. Example 4. What they say is, write parametric equations for the curve defined by. Write parametric equations for curve defined by. Okay? They give me the curve in rectangular. They say y equals x plus 2 with given definitions. With given definitions. Okay? They say for x. So they're going to give me 3 different ways to parameterize this curve. So the first one says ax equals t. X equals t. So they're saying that I'm going to let x be equal to t. Well, y is x plus 2, so since x is t, y would be t plus 2. So there's my set of parametric equations for that curve. When x is t, y is t plus 2. B, we're going to graph it and look at the differences in the graphs in a moment. B, x equals 3t. X equals 3t. But again, if I want y is whatever x is plus 2. X is 3t, so y would be 3t plus 2. There's a set of parametric equations when x is 3t. And finally, C, they say x is negative t over 2. Well, when x is negative t over 2, again, y is x plus 2. Y will be negative t over 2 plus 2. There would be my set of parametric equations. So writing the parametric equations for different parameters is pretty easy. Now, let's do an analysis and see what it's really doing. Well, I already knew, they say y equals x plus 2. Y equals x plus 2 is a straight line. X, y, 1, 2. Y equals x plus 2. When x is 0, y is 2. You're right here. Okay? When x is, so I'm just doing a quick t-chart in my head. When x is 0, 0 plus 2 makes y equals 2. When x is negative 1, negative 1 plus 2 makes 1. Negative 1, 1. So y equals x plus 2 is that line. Okay? Y equals x plus 2 is that line. Okay? Now, let's look at these different ways we can parameterize this curve. 1, 2, 1, 2. So again, and what I'm going to do is I'm going to look at t, x, and y. For this one, we're going to look at t, x, and y. For this one, then t, x, and y. For this one, okay? So I'm going to start at t equals 0. When t equals 0, x is 0. When t equals 0, y is 2. When t is 1, x is t, so x would be 1. Y is 1 plus 2, which would be 3. So 0, 2, right? And then 1, 3. And I'm going in that direction. So as t goes from 0 to 1, for this parameterization, this function will go from right here to right there. Okay? Let's do the same thing here. Let's do 0 to 1. When x is, or when t is 0, x is 3 times 0 or 0. When t is 0, y is 0 plus 2 or 2. When t is 1, 3 times 1 makes it 3 for x. When t is 1, 3 plus 2 makes it 5. So as t goes from 0 to 1, this parameterization starts off at 0, 2. Same place it did here. But it goes to 3, 5. And again, it's going in that direction. Okay? So we can see that with this parameterization, you're moving along this line way faster with that parameterization versus that one. As t goes from 0 to 1, this thing only moves that far. T goes from 0 to 1, this thing moves all the way from there to there. Let's check this dude. 0 and 1. When t is 0, 0 over 2 makes x equals 0. When the t is 0, 0 plus 2 makes y 2. When t is 1, negative 1 half is x. When t is 1 here, you get negative 1 half plus 2. That's 3x. So this parameterization, x, y, that's 2. Still starts off at 0, 2. They all did. Okay? But negative 1 half, positive 3x. This one goes from here to here, and this time it's going in this direction. They're all traveling along this line y equals x plus 2, but when you parameterize things differently, you can change both the speed at which you go along that plane curve, and you can change the direction at which you go along that plane curve. So different parameterizations will travel along these curves in different manners. Okay? And again, you have to sketch the curve, and you have to, tell me the orientation. Now, I should have just indicated that this thing keeps going both directions. I just did t from 0 to 1. Keeps going, right? Because in this case, for this parameterization, t can be negative or positive, it doesn't matter. Okay? T can be positive or negative. And the one we looked at earlier, t only could be positive. So again, that can change, that can vary quite a bit. Okay? On page 984, what can we do with these parameterizations? Well, they're pretty good. They help us out when we want to model certain things. And specifically, either uniform, linear motion, or the other times we can use it. And this is all on page 984, projectile motion. So these parametric equations come in really handy when we want to model both uniform, linear motion, or projectile motion. Uniform linear motion is exactly what it sounds like. You're moving along at a constant speed along a straight line, linear line. You're moving at a constant speed along a straight line. Projectile motion means maybe you had a cannon, okay? And you shot a ball or a cannonball out of it. Cannonball goes up, comes down. That's projectile motion. So again, parametric equations can be used to model both uniform linear motion or projectile motion. So, one thing we will say is that t be greater than or equal to 0. So this is on page 984. Read it. I'm only going to paraphrase. Read it. So this is modeling motion using parametric equations. So two equations, uniform linear motion, okay? The equation says x equals x naught plus AT y equals y naught plus BT, okay? Those are my two parametric equations for uniform linear motion, okay? And they say where A is the horizontal component of velocity and B is the vertical component of velocity, speed. Okay? So A is just how fast you're going in the horizontal direction, X is horizontal. B is how fast you're going in the vertical direction. X naught is just your initial position horizontally, Y sub 0. So X sub 0 is your initial horizontal position, Y sub 0 is your initial vertical position. They put the 0 because we're assuming that at time 0, that's where you're at. So X sub 0, subscript 0, means your horizontal position at time 0. Y sub 0 means your vertical position at time 0. Okay? These are my uniform linear motion parametric equations. Okay? So with that in mind, example 5. Example 5. And again, read this. I'm not going to write it all. Read it. I'm going to show you the equation. It's pretty simple. There's X, there's Y. Okay? They say that an ant is at 72.24. So let's say from here to here is 72 feet. Okay? And from here to here, I need to go up to maybe about 30. So right here, and they say the coordinates of that point are 72, 24. X coordinate is 72, the Y coordinate is 24. Okay? And these are inches. Inches. Okay? and B is at 0, 12. So suppose that's the point 0, 12. Okay? So what they said is there's an ant. An ant starts out at this point, 72, 24, and he's crawling along to here. He's going to crawl to the point 0, 12. Okay? It takes him 24 seconds. It takes him 24 seconds to crawl from 72, 24 to 0, 12. The ant starts out here at point 72, 24. X is 72, Y is 24. He crawls down to this point where X is 0 and Y is 12, and it took him 24 seconds to do it. Okay? And again, these are inches. Okay? So they ask me, they say write parametric equations for the ant's path, and they say assume everything is in inches. So write parametric equations for the ant's path. So A, parametric equations for ant's path. Okay? I want to write parametric equations for the ant's path. So I've got these two things. Okay? So again, x0 means what's its horizontal position at time 0. Y0, what is its vertical position at time 0? Well, he starts right here at 72, 24. So his horizontal position at time 0 would be x equals 72, x sub 0 equals 72. His vertical position at time 0 would be y0 equals 24. Again, x sub 0 means his horizontal position at time 0. He started out at 72, 24, so x sub 0 would be 72. Y0 means its vertical position at time 0. He started out at y equals 24. Now, I also need to know his vertical, horizontal, and vertical speed. Well, we know for speed, distance equals rate times time, right? So the rate would be distance over time. So for A is his horizontal component. A is the horizontal component. How far did he go horizontally from here to here? Well, X is the horizontal axis. So he went from 72, X equals 72, to X equals 0. So the distance is 72. Distance over time, he went 72 inches. And the time was 24. So his horizontal component of speed, his speed horizontally, was 3 inches per second. He went 3 inches per second. That's A. Okay? So let's write the units. 3 inches per second. Okay? Well, what's B? B is his vertical speed. Well, vertically, he went from y equals 24 to y equals 12. 24 minus 12 is 12. And it still took 24 seconds. That's 1/2. So we're done. X is x sub 0. X sub 0 was 72. Plus AT. A is 3. Y is y sub 0, 24. Plus B, T. One thing I forgot. He went from x equals 72 to x equals 0. So he was going down. So his speed, he went down 72 over 24. So this is negative 3. So that's a minus 3t. And, well, the x, he went backwards. In x, he went backwards. So that's why it's a negative 72. He went backwards, horizontal. The B, he went down 12 units. He went from y equals 24 down to y equals 12. So B is negative also. Negative 1/2. So be careful. Again, we have to consider directions. Those are the parametric equations. Those are the parametric equations. Okay? All right, so there are my parametric equations. Part B of the problem says determine the ant's location 8 seconds after leaving point A. So part B, determine ant's location after 8 seconds. Okay? Well, that just means that t equals 8. So all that means is take these two equations, put a 8 where the t is. So x would be 72 minus 3 times 8, right? Put 8 where the t is. Y would be 24 minus 1/2 8. Okay? 3 times 8 is what, 24? So that would be 48. 1/2 of 8 is 4. 24 minus 4 is 20. So that ant will be at the point 48, comma 20. He will be at the point 48, comma 20. All right. So that's how we can use these parametric equations to describe uniform linear motion. Okay? Uniform linear motion. Okay? The next thing we're going to do is we're going to write down the parametric equations that describe projectile motion. Projectile motion. So again, that let t be positive is still in play. So again, read these. So we're doing projectile motion now. So for projectile motion, parametric equations are x equals v sub 0 cosine of theta t plus x sub 0, and we'll talk about what all these things mean. Y equals negative 1/2 gt squared plus v naught sine of theta t plus y naught. Okay. So again, projectile motion. Think about a projectile. Well, with respect to the horizontal, a projectile will always be launched at some angle theta with respect to the horizontal. There's that theta. V sub 0 is the initial velocity. Okay? X sub 0 is still your initial horizontal position. Y sub 0 is still your initial vertical position. So again, theta is the angle. That projectile has to be launched at a certain angle with respect to the horizontal. That's theta. So there are my projectile motion parametric equations. So with that in mind, example 6. Example 6. They say you got a guy that's throwing a shot put. Suppose that's the x and y axis. We're going to orient this at 0, 0, okay? So he's going to release the shot put 2 meters. 2 meters. So this distance from here to here is 2 meters. And the shot put's going to go like this. So the shot put is going to be released at an angle theta. Okay? And again, the distance where he releases that shot put is 2 meters above the ground at an angle theta. Okay? So that shot put's going to go up, come down, and fall. Okay? They say the angle is 38 degrees. So theta is 38 degrees. Okay? And they say that the initial speed is 12 meters per second. So V, 12 meters per second. V sub 0. All right, so they want me to write parametric equations. So X is V0, 12, cosine 38 degrees, T plus 12. Y, negative 1/2, and again, this G is the acceleration due to gravity. So G can either be 9.8, negative 9.8 meters per second squared, or G can be negative 32 feet per second squared. Those are the two values for G. But since they're talking meters per second, I'm going to use this one, negative 9.8 meters per second squared. So negative 1/2, negative 9.8, t squared, plus B0. B0 is 12. Oh, this was X0. X0 was 2, right? B0 cosine t plus X0. It was released, well, no, X0 was 0, sorry. This part right here where the thing was released was at X equals 0, Y equals 2. So the X coordinate, the initial X coordinate, was at X equals 0. Now, this one, negative 1/2 gt squared plus V0, initial velocity was 12, sine of theta, so sine of 38 degrees, t, plus Y0, the Y coordinate, Y sub 0, that's 2. So we can simplify this one into Y equals negative 1/2 times negative 9.8 rather. We've already accounted for the negative, right? Yeah, this is not negative. Those are positives. But again, it's a negative 1/2, so that's why it's a negative. So this becomes negative 4.9 t squared plus 12 sine 38 degrees t plus 2. And again, I'm going to rewrite x. X is 12 cosine 38 degrees t. Those would be my parametric equations. And you could go ahead and get a decimal value for the sine of 38 times 12 or the cosine of 38 times 12. Those are my parametric equations. Okay? So that was A. B says, for how many seconds is the shot put in the air? How many seconds is a shot in the air? And you can look at rounding. They want you to round a certain way. You know how to round. I'm not worried about that. How long is the shot put in the air? Well, the Y, this thing for Y, my parametric equation is negative 4.9 t squared plus 12 sine 38 plus 2, t plus 2. Well, again, 12 sine 38, okay? 12 sine 38. We can plug all that stuff in. You can either take your calculator and do that. And let me go grab my calculator. Well, of course, I can't find my calculator. Let's see. Nope. I don't have my calculator. Doesn't matter. So, sine of 45 squared root of 2 over 2. Because 38 is pretty close to 4. I'm just going to get a rough guess of what this is. 0.7. 6 times 12, 6 times 2 is 2, carry 1, 7, so 7.2. I'm going to call that 7.2. So I'm going to say this is negative 4.9 t squared plus 7.2 t plus 2. I just rounded that to 7.2. It's probably 7.3, 7.4, but I don't really care right now. So this is a quadratic. So how many seconds is this in the air? Well, the y-coordinate tells you how high you are. So when this thing comes down and it falls and hits the ground, the moment it hits the ground, the height is 0. So I'm going to let y be 0. I'm going to solve this. Okay? Set it equal to 0. That's a quadratic equation. The a is 4.9. The b is 7.2. The c is 2. Plug that into the quadratic equation. Negative b plus or minus square root b squared minus 4ac all over 2a. Plug the a, b, and c into that. They say you'll get two answers. T is either 1.74 seconds or negative 0.2 seconds. But t can't be negative. Time can never be negative. So there's the time that the shot was in the air. It was in the air for 1.74 seconds. You're going to have to plug this stuff into the quadratic formula. That's just a little bit of arithmetic. So that's B. That's B. Part C. Part C. C says they want us to find determine the horizontal distance. Determine horizontal distance traveled by the shot. So how far did that thing go horizontally? Well, that's the x thing. So x is 12 cosine 38 degrees times t. But now I know what t is. That thing was in the air for 1.74 seconds. So all I need to do to figure out how far horizontally x he went, I'll just plug in 1.74 seconds. So I'll take the cosine of 38, multiply by 1.74 times 12. They say that x is 16.45 meters. That's how far it went horizontal. Okay? And then finally, D says, when does the shot reach its maximum height? When did it reach its maximum height? Well, this thing is a parabola, right? The vertex of a parabola tells you the maximum end. Now remember, the vertex of a parabola has two coordinates. There's an x and a y coordinate. The x coordinate of the vertex tells you where or when the max occurred. The y coordinate of the vertex tells you what the maximum end is. And if you recall, to find the vertex of a parabola, it's negative b over 2a, comma f of negative b over 2a. So the a, b, and c are still these things. So negative b over 2a would be negative b, but b was 7.2, over 2 times a, but a was 4.9, equals, if you do that in your calculator, they say 0.75. Because you got to round. And this was time. It reached its maximum height at time, 0.75. And they say the last question is, what was the maximum height? Well, what was the maximum height is going to be this thing. So I'm going to have to take my y-coordinate, because again, the y-coordinate gives me the height. The x-coordinate gives me the horizontal distance. So we know that the thing was at its maximum height after 0.75 seconds. So since y was negative 4.9 t squared plus 12 sine 38 degrees t plus 2, I'll just put 0.75 everywhere. Squared, every place of t, I put 0.75. okay? Do that in your calculator. And they say the maximum height is 4.78 meters. That's the max height. So that's how we use those parametric equations that describe projectile motion.